तेरी अच्छा हेलो श्रेयस। हाँ, वोट करने हैं 8 बजे। सही है। अच्छा भाई ठीक है। हाँ, सैप में हो रहा है। कहाँ पर वोटिंग कहाँ हो रहा है? कहाँ पर? गार्डन में है। हाँ 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 हाँ। कार्ड डिस्प्ले, अच्छा ठीक है ठीक। अच्छा डायरेक्शन दीजिए कहाँ जाने हैं भाई। मैं 7 से 9 बजे मुझे पढ़ाना होता है भाई, कहाँ पर दूर है क्या? 7 से 9 बजे मुझे पढ़ाना होता है मैं इंडिकेट पे। अच्छा 9 के बाद आ जाएगा, ठीक है 9 के बाद आ जाएगा। अच्छा अच्छा बाय। आंखें खुली हो या हो बंद, दीदार उनका होता है। आंखें। Good afternoon, everyone. Good evening. Yes. Good evening, everyone. So, one of the very important topic of expectation maximization and using expectation maximization for Gaussian mixture modeling. Okay. So these are the two topics. Okay. Uh, the questions here are easy, but the important thing is to understand the theory here in this case. Okay. So question you are able to do this time. You should present. Uh, so as I was telling, like you should be clear with the theory here of expectation maximization. Okay. And so the the theory actually basically stems from this. First of all, in the lectures only I've got this one. Uh, so the important part is that um, first you have to understand this, okay? And let's go to the diagram as well. Okay. So the our point was like so messages are coming. So what does text explaining? Okay, got it. Okay. So the diagram is like this. Okay. So pi is the parameter of the theta. Pi is the parameter of z, which represents the weight of the mixture actually. Okay. Z is the latent variable here. Okay. And theta is the parameters of the distribution. Okay. Of x. Okay. And so this is the diagram. Okay. And so for x you need to know this hidden variable pi and theta. Okay. To get to the final distribution here. which is the Gaussian mixture model. Okay, so just little light recap actually. Otherwise, okay. So this is the marginal likelihood for xn. Okay, it's like for one is for one sample we are looking at. Okay, IIDs has been considered here. Okay, and so this is the way they have defined. Okay, means this is the way it is. This marginal likelihood. This is prior multiplied likelihood. Okay, not prior. I think. Okay, let me see. So actually, this is just the probability theory. Okay, conditional probability into this Zn. Okay, sum over that gives the means you're summing over k. Okay, or k is denoted by the Zn. Okay, so Zn will not be in this result. Okay, like that. So it was actually one of that we had done as well. Marginalization is for parameter estimation, right? So removing the parameter Zn here. Okay, like that. And so they have represented it as the joint probability between xn and zn as well. Okay, sum over zn. So prior probability, and so the important part is here actually. It is the posterior of xn. Okay, with respect to zn. So just from Bayes rule, I mean it's nothing difficult here as well. Bayes rule, as you know, for so this probability is given by occurrence with respect to one Zn. Okay, means for one n. The summation is wrong here. I think j, it will not be j. Means if for it to be j, then these coefficients will be in the zj, xj, zj, like that, to up to k. Or am I to? Acha, acha, sorry. So yeah, it is correct actually. So k is the number of pulses over which it is summed. Okay, as you see here. Okay, not xn. Actually, just confused. Uh, okay, so what I was explaining is like to sum over the k values, that is the number of mixture model, number of Gaussian distribution we have. Okay, and so this is the posterior, that is the most important thing. Okay, so this can be represented as like this probability has been given as pi k. Prior probability is usually represented as pi k, and this. Okay, uh, so this is the y, z, and k. Okay, so this is the Gaussian mixture model actually, and so you iteratively. This is just the introduction. Model is here. So uh, so that we have to do it iteratively. Okay, first the log likelihood, and then set an initial value for this y, z, and k, the responsibility, and then keep updating the parameters. Okay, recompute the log likelihood. Okay, then from that compute this responsibility, from that calculate the update the parameters. Okay, like that it will continue till convergence. Okay, so okay, maybe now little bit of question answering. Where is there? So questions I saw are very easy actually, and so just a MLE question. Let me solve it for you. So let's see, insert. So the distribution here we have is the exponential distribution. Okay, and this is the PDF of exponential distribution probability density function, and this is lambda. So they have actually asked for to calculate the value of lambda for the x1 to xn data set that is given. Okay, so this is the thing actually. So this is the PDF actually, and it is actually continuous distribution. Okay, but what happens that was I going to show? Yes. So okay, let's go to the question. Question is here. So this the means like this samples are sampled from the exponential distribution. Now you have to maximize the likelihood of lambda. Okay, so okay, so given we are x1 till xn. Okay, so this fx in our case PDF can be written as uh, summation. So the so in our case means like for each x suppose t, it can be written as like lambda e to the power minus lambda xt. Okay, now likelihood is product over these all values, because from n equals to 1 to n I think. Okay, and okay, and what you're having here is that lambda, and okay, maybe you can write x, okay, like that, whatever, somehow you have to write. Okay, lambda x, maybe t actually better. So this is the likelihood function LF. Okay, now what you're going to do is take the negative log likelihood, or maybe at least log likelihood. Okay, so L r minus log likelihood of LF. So what will happen here? Acha. So first of all, like you can write this one as you see lambda multiplied n times, right? So that will be lambda n. Okay, and in the exponential you can change it as a summation over t. Okay, to n lambda e to the power minus lambda x t. Okay, so this is it. Okay, now taking logarithm, what will happen? N lambda, negative is also there. Okay, log of lambda. Okay, maybe not that clear. Okay, and this will become lambda, and summation over t lambda e to the power log of this, right? So log over e, this comes out, right? And this is should I have written wrong, I think. So this is minus lambda x t minus lambda xt. Okay, so this will become minus will come out, so this will be plus, and then we'll get xt. Okay, so this is the negative log likelihood, that is n log lambda summation over, and also lambda is independent, so lambda will come out. Okay, and so you have to take derivative with respect to lambda here. Okay, and see what you get here. uh, so let's see. So n, maybe on the next slide, MLE is actually very useful many times, because in this well, let me show you why ML is important. So where was I? Okay, so they have got this parameters mu k, sigma k, okay, like this, with MLE actually. Okay, as you can see, they have first initialized the log likelihood, and then get got this one. Okay, then with MLE they have got the mu. This formula for has came from MLE. You have seen from the lectures as well. So why MLE actually? And so another way to estimate this parameters is like, so likelihood is here. Okay, you take the prior, okay, and integrate it. Okay, and so what happens in the integration is that, uh, when you're trying to calculate the posterior, what happens is that whenever integrating, so you see that means the mu k, and this covariance matrix sigma k, means like, yeah. So like, what do you think? Suppose like, we have a uh, suppose we have, uh, okay, I think we have the question in here as well. Okay, so here we have question as well here. Let me show you. So this is a question actually, that if p dimensional Gaussian is there, then how many parameters we actually have that needs to be estimated. Okay, so the number is huge. Okay, and so let me show you how. There's nothing much actually. So from the Gaussian distribution, you know that mu vector that we use is like p dimensional vector. Okay, you can understand it like, we use p for the single case, well, means like means one mu for single case. For lot of that, if multi-dimensional Gaussian distribution, then what happens? Some let's see it out. F, nice. F is the answer. But the importance is like, this is p dimensional. Okay, so number of mu parameters is p here. Now you have the covariance matrix as well. So maybe little I will explain the covariance matrix as well. So covariance matrix is like, so you have, means the parameters here are what features. Okay, like that. Okay, so what happens is that, when you're calculating the covariance matrix, suppose for x1 till xn. Okay, and from here again from x1 to xn. Mm, nice. So what happens is that when you are calculating, when you're forming the covariance matrix, you are trying to means in these diagonals, as you see, x1 and x2, x1 and x1, x2 and x2, x3 and x3, like xn and xn. Okay, in that case, what you do is calculate the variance, as you know, summation over n x I square divided by n, right? So this is the acha, minus mu is also there, I think. Uh, Minus mu is also there, and divided by n. Okay, so this is the actually variance calculation. Okay, and what happens is that when you have here x2 and here the entry is x2. Okay, so when you need to calculate this one, that is x1 and x2, you need to calculate the covariance. So what is covariance? Let's see. Okay, what is happening? Too many things. Okay, so let me show you. So this is the covariance formula. As you see, covariance between two features is like over all training examples. Okay, what you do is you can see easy enough, right? So, uh, so this is the formula. So with each you calculate like this. Okay. Hmm? Oh, my cursor is not working now. Okay, so what happens is that for each this entries x1, x2, x till xn, and like that you calculate the covariances, and then you form this covariance matrix. Okay, so what we have here is that so as you can see, these are the covariances and these are the variances. So these are like oh, these are p values. Okay, n is the number of training examples here, so p is the number of features. Okay, or dimension, as you say. So this these are this where variance we are calculating is like p. Okay, so these are p. For mean this is p, for variance also p, but we need extra covariances. Okay, so one thing is to notice is that these are two are same actually, x1 and x2, x2 and x1 are same, as you can see from the formula. If you replace x by y, the result does not change, right? Is x or y, the result will not change. Okay, very easy to see as well. So what does it mean is that this right corner from the diagonal elements are repeated on the left corner, okay, of the diagonal. So so means like we need to only take one of these. Okay, and to calculate this, what you're going to do is that, so the total number of parameters is p square. Okay, now we calculate subtract the number of parameters, that is the variances. Okay, divided by 2. Okay, these are the number of covariances. Okay, okay, so this is the total number of parameters, comes out to be this one. Okay, so the a matter of the fact is that when, so you have lot of parameters. Okay, and okay, so what you see is that to estimate the parameters, what you do will what you will do is integrate with respect to those parameters. Okay, so what that would mean is that for to get the mean, you need to integrate over all values, all dimensions of the mean, and for like that. Okay, so that integration is like very hard or like intractable, as you say. Okay, so that is why ML is needed actually, because this posterior calculation to calculate the to estimate the parameters is not feasible in many cases. Okay, so now as we're moving, so this is the like log likelihood, and you take the lambda out as well, summation over t x t. Okay, you take derivative with respect to lambda. So what will that be? Okay, 1 by lambda, and lambda will remain here, summation over x. Okay, plus n log lambda. Okay, so this gets removed. Okay, and this becomes, am I doing right? uh uh, let's see. Acha, acha, this will be plus actually. That's why I got it wrong. Okay, because this is a product. Okay, while taking log, it will become plus. Okay, so now this is this one. Okay, and adding here is too bad. So n log lambda plus lambda times summation over xt. Okay, now what you have to do is take derivative and equate it to 0. N by lambda plus summation of x equals to 0. Got one negative here, I think. Is it right? Should has been negative here. Its answer should come positive. Acha, this one was negative actually. Okay, so this will be negative, and again this will be negative. Okay, so what will be the lambda now? N by x, summation over x. Okay, so this is the answer. We've calculated this one. We've calculated MLE many times actually. So this is another MLE question. I think you can do. Poisson's distribution You can do this one. Hello. I think you can, right? Emily, we have done many times actually. And so moving on. So the in the Gaussian mixture models, what happens is that we define the model. Suppose our probability distribution of x parameterized over some theta. Okay, that is equals to summation summation over k mu k and probability, that is one Gaussian distribution. This is one Gaussian distribution x mu theta mu and sigma. Okay, okay. So this is the form we have actually, and this mu, not pi actually. Okay, so pi actually here represents the weight actually that each Gaussian distribution has to be provided. So what happens is that if the sum goes is the sum, that is this one. Okay, if it is not one, then the probability distribution theory, what happens is that total probability needs to be one. Okay, that this does not get justified. Okay, and then if the sum is one, then each has to be less than one. Okay, so that is how you get this one. Cannot be zero. Once can be zero, but nice Ajay, nice Ritika. Means like cannot be negative. Okay, because means like negative weight has no meaning actually. It will be like penalizing other distributions, so that is not useful. Okay, so this is the idea actually. Gaussian just form actually, and maybe I should a little bit explain more actually. Theory is the most important part here. Implementation is can be called as hard, but like not anything extraordinary. So if you go like this one, okay, GMM, we've already seen the algorithm. Okay, but a little bit derivation here actually. I could not prepare for these actually. So as you see here, so this is the P that they have. Okay, that is the one I have defined here. This one. Okay, so they have written a likelihood over that. Okay, log likelihood, and they what they are doing is that they are, as I have said, is the sum over. Okay, this individual Gaussian distribution, and they have taken a distribution over latent variable z. This is what we call latent variable. Maybe you can so as you can see, the random variable zi indicate which of the k Gaussians each xi had come from. Okay, so which one had is come from, and with what probability or weight, as I said. Okay, maybe I can share the notes here actually. You can refer. Now why not able to add some words. So what was I explaining? Okay, so this is how you can write that pi that I have shown. You can write it like this. Okay, make a distribution out of that. Okay. So what we call this, like, and whenever we have an unknown, okay, in probabilistic methods, what happens, we make a distribution of that and try to learn the parameters of the distribution. Okay, so this is the idea. So that is why we have an unknown pi. Okay, to learn that, we have made a distribution and learn the parameters of the distribution to get the value of pi. Okay, so that is how it is. Now just taking logarithm property to get this. This is the loss function. So there here they have not explained, means like why they have to take MLE, because other methods of probabilistic method of this parameter estimations is very hard. Okay, lot of integrations. Okay, in discrete terms it is summation, but if the distribution is not discrete continuous, then it will be integration. Okay, so from MLE they get these values. Okay, for each, means for phi j we calculate it, then for mu j we calculate it, for this matrix also we calculate this. Okay, or as they have shown, there is a shortcut as well, like let me see. Okay, overall this is the thing actually. So they update these parameters, okay, according to the likelihood. Okay, and this is the one we have seen before. Okay, the posterior, not yes, the posterior of xi with respect to z. Okay, from Bayes rule. So like this is the, you can keep repeating to get the converged parameters. Phi j is the parameter of this zi. Sorry, some distribution. Okay, so we have to consider some distribution here as well. It's like otherwise cannot do it. Mostly they consider Gaussian as well. Okay, this is the Gaussian mixture model. Okay, and so next is expectation maximization. So what happens is that expectation maximization, maybe I should open this only, understand better. Theory, understanding the theory here is very important. Not working again. Where my cursor has gone wrong now. Expectation maximization. Yes. Okay, so as you see here, the first writing, explicitly finding the MLE of the parameter might be hard. Okay, uh, because the z's are unknown actually. Okay, latent random variable without any knowledge or any data. Okay, so EM algorithms is there as I said. Okay, and so what they have done, you can see. So they have considered another Q distribution over Z. Okay, so so this is the distribution we had. Okay, mixture model. and they have considered another q distribution, okay, and made it like this, okay, and taking the logarithms we get it like this. And now the Jensen's inequality, but not going to depth, okay, here. uh, so the summation of the q's distribution that we have is 1 because it is a distribution, simple enough. And going to the important steps, as you see, what we are doing is that for each steps, okay, we are updating the q values, then updating the parameters of the distribution, okay, m steps till convergence, okay. So in this situation what we do is that we model it as the means like what we do is expect we take expectation with respect to a known data, okay, and then take MLE of that, okay. So this is the one, okay, option, okay. And now what we have is that you try to maximize this, okay. This is the q that they have shown there, okay, same thing, okay. So you try to maximize this, okay, to get the as you can see e steps and m step. Okay, let me show again. We see nice, but little bit of understanding here, okay. So as you see here, we are updating the q, okay. In this case, it is this means as you can see the unknown, the known data, as I said, distribution over the known data, okay. Uh, and after that, for m steps, what we are doing is the updating the parameters like this argmax of, okay, okay, same thing but different notation, okay. So after that also what you have to do is to take the maximum uh, of the two parameter, actually the parameter that they have got, the higher one should be taken actually. So there is another optimization here, okay. The EM algorithm can be used for parameter estimation of mixture models. Can only be used. Acha, that's wrong. Can be used for many other things actually. And Gaussian mixture model for clustering algorithms always outperforms k-means and single link clustering. So you have to understand this one. Gaussian mixture models is a supervised algorithm. Okay, these are unsupervised. Okay, unsupervised always loses against supervised. Okay, got this one? Clear? Unsupervised models always perform worse than supervised method. Okay, Gaussian mixture models, what do you have? This supervised data you have, or at least some supervision you have, okay, as you saw in the previous slide somewhere, okay. So this is for the unknown parameter theta, and for known parameter theta m minus 1, maximizing the expectation. Okay, so this will be one, the answer. And soft clustering was like in the lectures as well, like just the probability means like I'm not determining which cluster it belongs to. Okay, I'm just giving a probability that this cluster it may belong to. It has a high probability of going there. Okay, with soft clustering, I'm not giving a hard decision boundary there. Okay, so these were some of the things actually, and
Can you show the last question? Last to last question. Second last one.
this one,
Yes, yes. Both the statements are false here.
yes. Second, what you understand, like some supervision, some supervised data is there in Gaussian mixture model, but K means are these are clustering algorithm, no supervised data. Okay, this is the reason actually. So, sharing this as well. So, so as you can see, if you revisit here, uh, so as you can see, just a little bit of further reading. So we have an estimation problem. Okay, we need to estimate the parameters. Okay, so that we can train and just infer based on those. Okay, so we have this parameter model. Okay, there is Z as well, which is represent the a. So you can see here means like we are not explicitly declaring whether this is a mixture or we need to cluster into different question models. Not like that. Okay, just a general as I was saying, just a general latent variable. This is latent variable, a hidden variable. Okay, so a hidden variable is there. Okay, on which the our real variable x depends on these parameters theta on which x depends on. Okay, so as you can see, x depends on z and theta. Okay, like that. But explicitly finding the MLE estimates of parameter theta may be hard. Here, the Zi are the latent random variable. It is often the case that if Zi's were observed, then maximum likelihood estimation would be easy. Okay, so like that they say. In such case, the EM algorithm give efficient or maximum. So efficient. So just the important thing is here. Okay, maximizing L theta explicitly might be difficult, and a strategy is to instead repeatedly construct a lower bound on L. Okay, so the likelihood that they have, okay, log likelihood, they're calling it by L. Okay, so they're always taking a lower bound on the L. Okay, means as the lower as low as possible at each step. Okay, they do it for each steps, and what they have got the lower bound, then they optimize on that lower bound. Okay, so this is how it is. Okay, so means what happens is that after the lower bound has been reached, it is quite like the GMM problem. Okay, and so this is the QI or summation, just a simple things. Okay, so as you see, they have modeled like this. Okay, dividing up and down. Okay, and so they have used Jensen's equality to get this one. Okay, you can read it yourself. Jensen's equality is the important thing. It's a little bit of here actually. Expect so the summation is here just expectation of the quantity. This okay, okay. So summation, as you remember, expectation is what? Uh, some quantity. Okay, and this AQZI are the with respect to which I'm taking the expectation. Okay, qzi. Okay, so this is the expectation. Okay, so if you see, first for this they have taken a lower bound, okay, with respect to the Jensen's inequality. Okay, then they say that the summation, okay, is just an expectation. Okay, okay, so what they do is that, as you see, expectation over qi, okay, of this, okay, like that. Okay, you understand, function this, some function, okay, over this expectation is greater than expectation over the function of this. Okay, like this. But these zi are the, okay, expectation we are calculating, drawing a zi from q. Okay, like that. So what we do is that when we sample zi from q, we calculate this value. Okay, we repeatedly do that and calculate the mean. Okay, that is the expectation. Okay, we sum those values divided by the number of values. Okay, that is how you get this expectation and you apply function here. Okay, another is that you calculate the expectation of this function like that. Okay, so this is higher and this is lower. Okay, so for any set of distribution q, whatever we q, formula 3, okay, gives the lower bound on L theta. So you get a lower bound. Okay, so now they're looking for a tighter bound for the for a particular value of theta, and now the m steps part comes actually. So they have considered c, and now, okay, this to be c, as you see. Hmm. And what they're doing is that, okay, so proportionality. Okay, okay, q is proportional to this. And so what they did is, like, you can see this qzi. Okay, they have considered it like this. Okay, so they have considered it as the, as you can say that, what do you call that, just forgot, the responsibility. So they take the q as the responsibility in this case. Okay, now we simply set the q to be posterior of the zi, given xi, and setting of the parameter theta, posterior of the zi, posterior of the xi, maybe wrong here. As you can see, this is the posterior of xi. Now for the choice of the qi gives a tighter bound. As you can see, this is the e step in which m steps. This is the e step. Okay, in the m step of the algorithm, we maximize the formula in equation 3 with respect to the parameter to obtain new setting of the theta, repeatedly carrying these steps. Okay, so they are repeatedly carrying these steps. Okay, so what happens is that you got this one q. Okay, we put this value of q here and take such value of theta which maximize this. Okay, now you take value of theta here. Okay, q gets updated. Okay, and then then what you do, take this q and then it repeats over. Okay, okay, like this is actually. So you can actually use em for Gaussian mixture as well. Okay, so that was in the videos as well. Not going to into that depth here. Okay, so thank you very much everyone.
Sir, can you explain the last two questions? I didn't understand why these both the statements are false.
Acha,
And what about the hard clustering?
hard clustering. This one, huh?
Yes, this one and the second
So
last.
like hard clustering is nothing like extraordinary anything.
As we understand, slop clustering means the samples can be
Huh.
clustered
So
in
in
any cluster.
in GMM, what it is it like? You have different Gaussian distributions. Okay. So what I am saying is like, and Gaussian distributions are shaped like this. Okay. So which distribution does it belong to? Okay. So this is what we mean by clustering in case of GMM. Okay. So in case of GMM, this pi that you had, okay, was the probability of occurring in that class, or in that means the point being part of that Gaussian distribution. Okay, so this is pi is that probability, pi k, as you were having. Okay, you used to model this pi k, used another uh, variable z, that is a latent variable, and you had a parameter. Parameter is what they said pi. Okay, it's like a little bit here and there. So okay, so you model another uh, okay, z latent variable with having another parameter. Okay, for that. So this gives the probability, the way it gives the probability of occurring in that class. Okay, and hard clustering is what you can understand, like, I'm not saying by probability, I'm saying that which class it belongs to, which distribution it belongs to. So how do I do that? How do I do that is like, suppose you have several probabilities. You've got 0.9, 0.05 uh, belonging to another class, and then suppose the third class probability is also 0.05. So some should sum up to 1. Okay, so
So
from that,
hard clustering means it belongs to any particular cluster
huh.
and it is
So
definite.
and you see
And
how it
top
has,
clustering it will be the probability it belongs to any cluster. Is it?
and you have to understand like how I'm doing hard. I can do hard clustering for GMM as well. So from this, from the modeling part, you get the parameters pi, means like the weights, and also the theta, and these are all the parameters you'll get. Okay, by training in that. So from the pi, you see the maximum probability is this one. Okay, so as I said, it is the one. So what we have to do in this case is just take the maximum of all these. Okay, and whatever will be the answer is the hard cluster. Okay, means like I'm taking giving a specific answer. Okay, okay, and
Okay.
so this actually comes from this one only. Can only be used for parameters estimation of mixture models. So in this, while I was showing you, they have not considered any like mixture model type. In mixture model, what will happen? This pz that you have, okay, will be, okay, uh, means like, means what happens is like pz can be like probability. Okay, and the other distributions we have are the like the classes. Okay, so this is the uh, uh, mixture modeling case. Okay, but this z can represent in a general case anything. Okay, and they have also not considered z to be anything. Okay, means like probability, means the pz giving probability like that. So z are just latent random variable. Okay, latent variable is just like a hidden variable. Okay, on which the our main variable depends on, like that. Okay, nowhere they have mentioned that it is mixture model questions. Okay, in mixture model, what will happen is that you can divide this. okay, p xi and z p zi, okay, and you can say that sum of p zi, okay, is equals to 1, okay, and each are less than 1, okay, but they have not considered anything like that. Here they've introduced another distribution, and on that they have considered this one, okay. Okay, so that is the means like what happens, you read it after GMM, so maybe you can consider like EM is for GMM, but there is nothing such assumption, okay. And Gaussian mixture model is supervised, so that is why it performs better, others are not, okay. Simple enough here.
What about the second one? I didn't hear you. I didn't hear.
Acha, as I was saying, like Gaussian mixture models are supervised, okay.
Okay, supervised.
Supervised, you understand? Let me
And for the first statement, if it is in Gaussian mixture, then it will be okay.
uh, but
If it is
for
saying
expectation
EM for the
maximization,
Gaussian,
for expectation maximization, there is no consideration of mixture of Gaussian. As you see here, they divide it like this. Okay, they will say like this will uh, sum up to 1 like that. Okay, okay. So what happens is that now, as I was explaining, what I was explaining. Acha. So you have training examples here. Okay, as you see, M. Okay, and for each of them, so you're training over all of them actually. Okay, so that is the reason. Okay, thank you.
Sir, I have one problem
What problem?
in the regarding the week 10 assignment.
Acha, let's see.
The question number 3.
Acha, this actually we had discussed it. What is the query?
No, no, question number 3.
Yes, query 3.
Uh, Complete link clustering.
Acha,
Question number 3.
this is not the one. Huh?
The previous one.
Acha, previous one.
This one.
Hmm.
The answer option is incorrect. Is given in the solution.
This is not the
Same
one.
answer. Same answer is given for single link clustering and the complete link clustering.
So what do you think is the answer?
In the I think the option D will be correct.
How?
I also gave the D answer. I also solved and I got the answer D, but it is showing answer B.
How is it?
So after calculation, the maximum distance between the points and which has the minimum distance among these maximum distance, those groups or those pairs will be merged first
Maximum distance.
in the complete link.
Acha, what do you say?
First P3 P4 must be merged, then
P3,
P5,
P4. Acha, okay.
then P5 P6,
P5, P6. Okay.
and then P3 P4 P5 P6 will be merged, and
Acha,
P1 P2
here
is
what you're
separate.
doing? P3,
Okay.
P4, P5, P6. You're doing the same thing actually.
G.
So what's the difference? Like P3,
P3 P4 pair and P5 P6.
P5, P6. Yes. Then P1,
Yes.
P2.
P1 P2 separately merged and then combined with P3, P4, P5, P6, and then P1, P2.
Uh,
This is option
Acha,
D.
so you have the doubt here is like this should not be connected first, right?
It is not correct.
Acha, so what is like the situation is like P5, acha, 3, then we have 4, right? 4 is this one. P1, P6, right? Acha, P1, acha, P1, P6, and this should be the answer, no? This
Uh,
should be.
it is wrong
How?
because first we merge the minimum distance, that is 1, P3 and P4.
Okay,
Then we change the distance matrix. As per the complete link, we consider the maximum distance between the points and the pair,
acha,
individual points. And then it comes out the P5 and P6 then merge.
acha.
After again, after merging these 2 points,
Hmm.
then we reassign, reevaluate the distance matrix. And then again consider the maximum distance between the points. Then it comes out the P1 and P2.
So you are taking the minimum distance, right?
Not maximum,
How maximum?
because in complete link clustering we consider the maximum distance, and in single link we consider the minimum distance.
So what you're doing here? P1, P2 is not the maximum, like 9 is 10. What you're saying?
After reevaluate the distance matrix, then we find out the P1 P2 has the
Acha, acha.
minimum
Okay,
distance.
okay, okay. Got it, got it.
After
So
that, after making the three pairs, first P3 P4,
acha,
then P5 P6, and then P1 and P2.
okay,
After that we reevaluate the distance matrix, then P3 P4 and P5 P6 will be merged first, and then
acha.
after
Wait, wait.
P1 and P2.
So P5 and P3, P4, as you're saying. So P3, P4, this one.
See the D, option D,
Acha,
this one.
acha.
So I am getting this particular clustering. P3 P4 first, then P5 P6,
So
then
I'll have to
P1.
see actually and maybe correct that. Okay. Okay.
So consider this if reevaluate and recheck this particular question.
Okay. Sure. 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 I'll do.
And one more problem in the same assignment, the question number 7, the RAND index.
Acha, this one. So you have to run a
No,
code
no,
book.
no, no, no. I think this assignment is not which is given to us.
Acha, acha, yes, it's the old one actually.
Uh,
One.
uh, Assignment 10.
This is the one. This is the one, right? Huh?
I think it is this one. Question number 7. Yes, yeah.
The rand index can be used as true positive and acha, p can be true negative. We're going to
So
constant.
I have seen in the Wikipedia. So this one is given. I post it on the message box.
Yeah.
So it is given similar to the accuracy. True negative plus true positive divided by true negative plus true positive plus false negative.
Acha,
So I think it RAND index similar to the accuracy.
acha, acha.
No, I think it's A plus B divided by N accuracy formula. A plus B plus total parameters.
This is n actually. It's n.
It should be N in case of accuracy.
Acha, in case of accuracy.
So
Acha,
it should be accuracy equal to RAN index by 2.
acha, acha. Okay. So rand index, as I say, is Yes, we're prior to this. Okay, okay.
So
Let's.
can you give some hint for this week assignment question?
Acha, okay. Let's see. Uh,
Week 11.
so, so expectation maximization for Gaussian mixture models. Okay. So just let me read this one. Like that when you see the video, actually, video is easier. Okay. Number of components, mixture coefficient. Okay. Mu k, covariance matrix of each component. Okay, like that. See and do it yourself. Actually, responsibility terms. Okay. So what is the responsibility term here? Is it true about the responsibility term? Yes, the sum over k will be 1. Acha, I will not say. Okay. So as you see this slide, actually, it is very easy to infer from this. Actually, this is the responsibility you have. Okay. Okay, and a sum over. Okay, you sum over something and see what can happen. Actually, sum over k and sum over n. Okay, and then this is 0 and 1. 0 between 0 and 1. Okay, so should it be between 0 and 1? It should be, right? Okay, and so this is not 0 and 1. Acha, only 0 or 1 actually. Acha, this is the one. So this is not be correct actually. And if this is, then this will not be the case actually. Acha, can be the case actually. So this is actually the expression you have. Okay, if the for two different z and k values are varying. Okay, so very easy to see actually what will be the one. Okay, from this slide actually, see, this slide is enough actually. Just start the video and this is shown to you actually. Just freeze and take a screenshot like me. Okay, write the update equation from uk in the email algorithm. Okay, so update equation actually, so you have to just see. Okay, so what do you do is like, okay, very similar actually given here. So okay, so b, okay, you see here, you see this is the Gaussian mixture models in email algorithm. Just stops here. Okay, you are, this is also from the theory only about correct statement. Okay, mth iteration, this is a computer using parameter estimate. Just the theory you have to see again. Acha, here the coding part actually. So you have to use sklearn. So from sklearn model, actually, there you can means get the uh, GMM actually. Okay, you can Google search here sklearn GMMs, and from that you can do it. So this is the documentation as you see. So number of components. Okay, so what do you have given? Two components. Okay, with random state 0, do not change the default parameter. Fit the GMM. Acha. Okay, And just see some codes, I think, Geeks for Geeks, how they do it. They loaded the data set, the covariance types, filtering with GMM models. That is how they are fitting the data here, okay? For each covariance types. Okay. So just this, seeing this one should be enough, I think. They've done it. Okay. Compute the log likelihood of the following points. Acha. So you have to see the log likelihood, okay, for this points, okay. So log likelihood, actually what happens is that you need to know the likelihood for that, okay. Okay. So for knowing the likelihood, what happens is that you need to know the values of number of components is given mu and sigma, okay. If you know the mu and sigma, component is already known, then what will happen is that you can calculate the log likelihood given a okay, and which has the highest likelihood becomes sampled from the model.
This is also from coding, sir. 5, 6, 7 from coding.
Acha.
If you see in the question number 5, then you can.
6 you're gonna do by hand. Acha, model trained. Acha.
5 to 7 are from coding.
Uh, model trained. Now to use that one from the code actually easier. Or can be done by hand as well, I think. Okay. That model be a GMA with two components of training question. Acha. Okay. Last question. GMA with two or more components likelihood can attain arbitrary high values. Arbitrary high values. Two or more components. The likelihood increases. B statement B is correct. That's for sure. GMA with two or more components likelihood can attain arbitrary high values. Any ideas here? 8 statement A. Not audible actually. We were saying
B is correct, you think.
B is correct now. A and A. What do you think? A likelihood can attain arbitrary high values. Oh, well, it doesn't look like that. They were experienced like that. Two or more components should not be the case actually. Arbitrary high values. In calculation, it can happen. In calculation, what happens is that when you're coding, that multiplying the likelihood actually means that the values are very small probability as you see, and because the independent, okay, independent training examples, okay, so multiplying over these actually they can go to zero actually. That is what can happen actually, but very high values is like very hard actually. The coding time, what happens is they can go to zero, okay. So for numerical stability, what they do is that they take log likelihood and they take some stabilizer so that it does not go to zero, remains a small value, okay. So maybe you can remember as well during coding time. This can happen means you're fitting directly from a library, but if you do it yourself, define the model yourself, then these problems are there actually. You're summing of the probability means like your product over the probability likelihood, it can go to zero. Serious problem actually. Okay, so these are one of the things. Okay, thank you very much. Okay.
So, sir, 1 minute, sir. Sir, you have suggested one probability NPTL. I forgot the name. What was that one?
Acha. Probability is very important. Okay, and the course is
Yes, for thermal.
no, this is not the course. This is not the course. Maybe I should provide a link. On YouTube as well. Let me check first. Is this the one?
Please, please share the link in the chat.
Probability is very important for my student. Okay.
Okay, thank you, sir.
Thank you very much.